Hi everyone, my name is DauHongQuan, class Industrial Informatics with the advisor Trần Thị Anh Xuân. I am very glad to defend my graduation thesis today. So now I will give you my presentation of my thesis, which is study on a linearization technique for power amplifier in base transceiver station. First of all, I want to give you the objective and the contribution of my thesis to help you follow the content of my presentation. The objective of the thesis is study on predistortion technique for linearization of power amplifier in base transceiver station, and the contribution is for study on the theories of nonlinearity and predistortion technique. Second, simulate and evaluate predistortion in communication system, and thus integrate a commercial predistortion solution into a real application. I will start my presentation with the outline here. My outline has six main parts. Part 1, Introduction. Part 2, Nonlinearity of Power Amplifier. Part 3, Linearization Technique Predistortion. Part 4, Predistortion Simulation. Part 5, Commercial Predistortion Solution. And finally, Part 6, Conclusion and Future Work. Part 1, Introduction. First, I want to talk about the overview of power amplifier in wireless communication system. In wireless communication system, a base transceiver station is a very important equipment that facilitates wireless communication between user equipments and a network. I have here a simplified block diagram of a base transceiver station. In the transmit path, the digital data is first processed in digital baseband processor and is converted to analog signal by the AC and it is filtered to remove the out-band noise. And we have here an IQ modulator to upconvert the baseband analog signal to the RF signal. The RF signal is then amplified by a power amplifier, and an antenna will radiate the RF signal into space. So what is the role of RFPA in base transceiver station? Power amplifier increase the power of input RF signal to a significant power so that the RF receiver can send this signal. As we can see in this figure, power amplifier is the most power hungry block in base transceiver station. So its efficiency determines the overall efficiency of base transceiver station. So why do we need linearization for power amplifier? Because there are three major performance metrics of communication system. First is linearity, preserve the quality of transmitted signal and avoid any loss of information. And second, spectral efficiency is number of bits per second that can be transmitted in the unit bandwidth. So in modern telecommunication, new transmitting formats such as QAM, CDMA, OFDM are employed to achieve a high spectral efficiency, and then signal will have a high PAPR. PAPR stands for peak to average power ratio. And third, power efficiency is a very important consideration that affects deployment, operating cost, and environment. Unfortunately, power amplifier has trade-off between linearity and spectral efficiency versus power efficiency, as we can see in this figure. If we want the input signal work in a linear region and has a high spectral efficiency with high PAPR, the power efficiency of the PA is very low, approximately 10%. And if we want a higher power efficiency, the linear region must be wider. So the objective is design a PA system meets the linearity and spectral efficiency with the highest possible power efficiency. And in order to achieve this objective, we need to understand the nonlinearity of power amplifier. Nonlinearity of PA comes from distortion including intermodulation and memory effect. We can see in this figure a two-tone signal at the frequency f1 and f2. After power amplifier, other intermodulation terms will appear. For example, third order intermodulation will appear at this frequency and this frequency. And the fifth order intermodulation will appear at this frequency and this frequency. With the RF signal, intermodulation terms appear at frequency near the input signal, so they cannot be filtered. And memory effect can be explained simply by the fact that output of the system is a function not only at the corresponding input instant, but also of the other inputs at other instant in the past. So how does distortion impact on our communication system? It has two main impacts. The first impact is on signal spectrum. We, I have here an input signal spectrum, and the ideal output signal spectrum must be similar. But interpolation will make output signal spectrum regrowth like this. And then memory effect will make a symmetric output spectrum like this. We can use the adjacent channel leakage ratio to evaluate the impact on signal spectrum. The ACLR formula is here, and the higher value, the greater impact. The second impact is on a signal constellation. I have here an input signal constellation, and the ideal output signal constellation must be similar. But interpolation will make output signal offset like this. And then memory effect will make the dispersion of output signal constellation as illustrated in this figure. We can use the error vector magnitude to evaluate this impact on signal constellation. The formula is here. And again, the higher value, the greater impact. We also need model of power amplifier. Model of power amplifier can be classified into two types. Static nonlinearity model, which only describe distortion without memory effect, and dynamic nonlinearity model, which includes memory effect. And in static nonlinearity model, we have Salem model, Taylor series, and etc. And in dynamic nonlinearity model, we have a Volterra series and reduced Volterra series. For example, memory polynomial and generalized memory polynomial. In the next part 3, linearization technique predistortion. First, we talk about the concept of predistortion. The concept of predistortion is very simple. We have here a nonlinear characteristic of the PA, and a predistortion circuit, namely predistor, is inserted before the PA. This circuit inverts the nonlinear characteristic of the PA, so the total system will have a linear characteristic. So why do we choose predistortion amongst many linearization techniques? I have summarized a comparison of linearization techniques, for example, feedback, feed-forward, and predistortion. And compared with other techniques, predistortion technique has a lower complexity and high power efficiency in the wideband systems. So we choose predistortion. And we need to know how to do predistortion for a signal. In order to perform predistortion for power amplifier, there are two elements for it to build. The first element is a predistor block. We have to choose a model for predistor to create a predistor function. And when we have predistor block, we need to calculate coefficient for this predistor. And in order to do that, we need to have an adaptive architecture and an algorithm. If a power amplifier ignores memory effect, it can be modeled by using Taylor series. But when the signal is RF and the bandwidth increases, memory effect should be taken into account. So Volterra series can be used to model the nonlinear system. The kth order kernel includes a possible combination of a product of k time shift of input signal. So it includes all the possible forms of memory effect. So, but however, it resolves in a large number of coefficients and increase the computational complexity. Therefore, in practice, we use a reduced Volterra series model like a memory polynomial to overcome the computational complexity and while still describe memory effect. And when it comes to calculate coefficient, we need an adaptive architecture. And first, the direct learning architecture. In this kind of architecture, the PA model is identified first by using the yn signal as input and zn as a output. And then the function of predictor is built by inverting the PA model. However, the metric inversion is a complex computation, so I don't use a direct learning architecture. Instead, I use indirect learning architecture because in this kind of architecture, the function of predictor is built by identify the post-invert function by using Zn as input and Yn as output. And in terms of algorithm, I use three algorithms: least mean square, recursive least square, and recursive prediction error. Three algorithms try to estimate the least square solution, but each algorithm tries to estimate the autocorrelation and intercorrelation in different ways. We have a least mean square, we have a recursive least square, and we have a recursive prediction error. And in the next part, predistortion simulation, first I describe the simulation process. System with predistortion in simulating has for main block signal generator, predistor, power amplifier, and a coefficient calculation block. I simulate power amplifier by using Saleh model for PA because with this model I can easily adjust the nonlinear characteristic of PA. And I also use the reduced Volterra model for power amplifier because it describes the memory effect. In a signal generator, I simulate a 60-QAM modulated signal with the 100 MHz bandwidth. And with predistor, I simulate with a reduced Volterra model. And with a coefficient calculation block, an adaptive indirect learning architecture block is simulated. And this coefficient calculation algorithm I simulate with three algorithms: least mean square algorithm, recursive least square algorithm, and recursive prediction error algorithm. And after the simulation process, I have the results. In experiment A, signal spectrum with the BA Saleh model at the input power minus 12 dBm, we can see the spectrum regrow with the output PA without predistortion is the orange here. And three algorithms do improve the ACLR of the output signal, but the recursive least square and recursive prediction error methods are better than the least mean square. And when the input power is minus 18 dBm, the least mean square become worse, but the recursive least square and recursive prediction error still work well. And at input power minus 16 dBm, the the least mean square algorithms no longer converge, but the recursive least square and recursive prediction error still work well. At minus 14 dBm, recursive become worse than the recursive prediction error. And at input power of minus 12 dBm, the recursive least square no longer converge, and the recursive prediction error still work, but the performance becomes worse. At minus 10 dBm, the RPM does improve the ACLR. And with the signal constellation in experiment A, Without predistortion, the EVM is 14.5%, and with the recursive prediction error, the EVM is 5.6%. And the same with the recursive least square algorithm, and two algorithm improve about 11% with the EVM. And in experiment B, signal spectrum with the PA reduced Volterra model at input power minus 23 dBm. The ACLR without predistortion is about minus 23.2 dBc. With least mean square algorithm, this algorithm does not improve the spectrum growth, as you can see here. But with the recursive prediction error, the ACLR is minus 25.6 dBc. And with the recursive least square algorithm, the ACLR is minus 25.5 dBc, and recursive least square and recursive prediction error improve about 3 dB. And with the signal constellation without predistortion, the EVM is 17.5%, and with least mean square algorithm, the EVM is 9.3%. This algorithm improved 8% of EVM, and with the recursive prediction error, the EVM is 6.8%, and with the recursive least square is 6.6%, and two algorithms improve about 11% of EVM. So I summarized all the results and build a comparison table of three algorithms. The least mean square algorithm has a lowest complexity with in three algorithms, but the performance of least mean square is very weak. And least square and recursive least square and recursive prediction error are comparable. So I have a conclusion in simulation that the prediction with indirect learning architecture and reduced Volterra series model and three algorithms do improve the quality of signal. And the recursive least square and recursive prediction error are comparable and outperform least mean square. Part 5, commercial predistortion solution. When I take an internship in Viettel, I have a chance to approach a commercial predistortion solution. It is SC1905 Maxim. It is a digitally assisted analog IF predistortion solution, and it uses the reduced Volterra model to model the predistortor. And I can programming its parameter through SPI standards. And I set up here a test pen to evaluating the performance of SC1905. And I have the result here. Without this solution, the DBC is about 27.8 dBc, and with SC1905 the ACLR is 34.4 dBc, and SC1905 improved about 7 dB. So I can conclude that the SC1905 using reduced Volterra model to improve the ACLR of modulated signal. And so we can conclude that predistortion with reduced Volterra model will work in reality. So finally, in the final part, conclusion and future work. I have a conclusion here. Predistortion with indirect learning architecture, reduced Volterra model, and three algorithms to improve the quality of signal. The recursive least square and recursive prediction error are comparable and outperform least mean square. SC1905, a commercial predistortion solution using reduced Volterra model to improve the ACLR of modulated signal. And I have future work to do. In the future, I will optimize all the algorithms for better result. And besides, I will study on different types of linearization techniques, models, architectures, and algorithms in addition to those proposed in this thesis. And I will deploy pre-disaster models, architecture, and algorithms on real circuits using technologies like FPGA to uh, affirm this performance in reality. So this is references, and thank for this ends my presentation. Thanks for listening.